Everything we've been doing up till now has led up to this point where we can take a balanced equation that you know how to do now, and we can take inputs. Like we can say, all right, I want so many grams of this reactant, so many grams of that reactant, and I want to know what the end product is. How much can I theoretically produce as a product, or multiple products, depending on the reaction. So that's where we're headed in this discussion. First of all, we've got to know how to determine the formula mass. In other words, when we have a correctly written formula for a compound, what is its mass? And first we're going to look at atomic mass units, but they're not very useful. Right? So we're going to pivot from there to something a little more useful. It's coming. But this slide simply says that if you have this particular compound, which is what? Remember how to name compounds? Right, tin and fluoride, right? Type 1 or type 2. So, which one is it? A 1 or a 2? Well, you look at your periodic table. Does it have more than one possible charge? Yeah. It's a metal, nonmetal. And tin, since fluorine is always a -1, and you got 2 of them, then this one has to be a 2+. No other choice. So we say, there's the charge. Tin 2 fluoride, that's the compound. What we want to do is say, all right, we know how to determine the mass of that atom in atomic mass units. Just look it up. Look it on the periodic table. So tin, they're kind enough to give it to us, is 118.71 atomic mass units. 2 fluorines would be 2 times 19 atomic mass units. And the mass of that compound, 1 atom of tin and 2 atoms of fluorine, is just the summation of that. Okay. 156.71. Atomic mass units. Okay. No mystery there. All right. So what's the formula mass of H2SO4? What is H2SO4? Anybody remember? Let's say H2SO4 in aqueous solution. Starts with a hydrogen, right? So maybe it's an acid if we put it in solution. I think I'm going to use differently. I'm going to use a brand new one. And it's got oxygen in it, so we don't start with hydro. We just take the sulfate part. Yeah, H become X, sulfuric acid. Okay, what's the formula mass for this thing? Well, we've got 2 hydrogens, right? We got 1 sulfur. What's sulfur? 3206, I think. Unless my eyes deceive me. And then 4 oxygens. All right, so that'd be 3264. Right? 64 for the oxygens, 32.06 for the sulfur, and 2.02 for both the hydrogens. And I get 98.08. Atomic mass units. For this formula, assuming we're only counting 2 atoms of hydrogen, 1 atom of sulfur, and 4 atoms of oxygen. Okay. That's what atomic mass units refer to, single atoms. So it's approximately 98. All right. But like I said before, that's not convenient. We can't do anything with that. So what we need is a measure of the mass of so many atoms, or of so many formula units. Like we have one of those formula units. How much does it weigh? Well, it's going to be pretty small, correct? In grams, very, very small amount. So we're going to have to invent a counting number that will give us enough of those atoms to where we can get a weight on one of our balances, right? And that magic number is called the mole. The mole is just a number, and it's equal to 6.022 times 10 to the 23rd things. Could be atoms, could be molecules, could be ions, could be chickens. It's just a mole. That many is a mole. Okay. There's the definition, right? But it's not much use unless you know what to do with it. So if you have a mole of any one of those elements up there, they're atoms, then the mass is that number in the upper left-hand corner, right? For carbon, it's 12.01. So if you have a mole of carbon atoms, 1 mole, that equals 12.01 grams. So what we're talking about here is molar mass. How much does a mole weigh? Molar mass is that many grams per mole. And remember, if you have an equivalence, you got a conversion factor, right? Okay. We needed a standard though, right? And I picked carbon because carbon is the standard, only it's not all the isotopes of carbon. It's just one isotope of carbon, carbon 12. Carbon 12 is fixed by international agreement at 12.000, as far as you want to go, grams per mole of that isotope. And by the way, that's the abbreviation for MOLE. Don't ask me why. I just drop the E, and that's the same as the mole. So by international agreement, these isotopes, if you have this many of them, 1 mole of that isotope, it is by definition 12 grams exactly, with infinite number of zeros. And from there, everything else is compared to that. Now, why did I just say that 1 mole of carbon is 12.01? It's because naturally occurring carbon is not just 12, right? It's got some 13s in there, right? 13 mass numbers. It's got some 14s, although they're radioactive. Remember, carbon 14, radioactive. And there's some others. So the weighted average of all naturally occurring carbon, if you have a mole of those isotopes, and you don't know, right, what you have, but on average, they will be 12.01 grams. Okay. And that's nice of whoever did this, right? Or whoever does it continuously. Actually, the periodic table is periodically updated. And it takes into account new determinations of the isotope mix in naturally occurring elements. So as chemists, we don't have to deal with the isotope thing. We just know that if we have a naturally occurring source, which is anything we use actually, then 1 mole of that element's atoms will be that mass. Okay, and I usually round the mass to 2 decimal places. That's sufficient. 2 decimal places, they never change. right? Over time, when these guys that spend their whole lives doing these isotope ratios determine new masses for a mole of the element, it's always in the 5th or the 6th or the 7th digit decimal place. So if you round to 2 places, you're safe forever. All right. How many eggs does 1 mole of egg contain? Well, obviously, the definition, 6.02. I do like 0.022. I use 3 decimal places for the mole. It just helps, it prevents rounding errors. Okay, so this is the molar mass. The molar mass of naturally occurring carbon is 12.01 grams. Nitrogen is 14.01 grams per mole. Carbon dioxide is just the summation of the molar masses of the elements in its formula. So 1 carbon is 12.01. 2 oxygens is 2 times 16 is 32. So 32 plus 12.01 is 4401. That's the molar mass of that formula unit, CO2. So if you have 1 mole of CO2, how many moles of carbon do you have? 1. How many moles of oxygen do you have? 2. Yeah, it's not a trick question. All right. So calculate the mass in grams of a 2.5 mole sample of ethane. All right. We're going back to dimensional analysis. You know, when we first started this stuff before the first exam, I hope I told you, learn how to do it because you're going to see it again. We've got 2.5 moles of ethane. So what's ethane? Well, they give you the formula there. It's 2 carbons and 6 hydrogens. That's the molecule. So if you have a mole of these, or you have 2.5 moles of those, what do we need to convert from moles to grams? Right? Moles on the bottom to cancel, grams on the top to be our answer. Whenever you see grams and moles like that in a quotient, that's molar mass. Even if they're flipped, it's still molar mass. It's just you put the grams on the bottom sometimes if you're going for moles. We're going for grams, so the grams are on the top. But we need to know what's the molar mass of C2H6. So you got 2 times 12.01 grams per mole carbon, and 6 times 1.01 for the hydrogen. All right. So let's see, that's 2402, and 6.06 is 30.08 grams per mole. So we put 30.08 up here, and moles cancel. That times 2.5 gives us 75.2, 75. Well, we only got 2 significant figures there, right? But my calculator tells me 75.22. But we only got 2 significant figures, so we have to round it off to 75. So that's how many grams of ethane you have if you know that your container has 2.5 moles. It's a gas, so it's got to be a container. Well, they say 30.07. But it's still 75 grams. Okay? Dimensional analysis. How about the number of moles of 50 grams of water? So now we're going to have a different situation here. In this case, we've got the mass and we want to know the moles. Oops. That we have 50.0 grams of water. So we want moles here That means grams on the bottom to cancel that grams and moles on the top. So in this case, we take the molar mass and just flip it, right? Remember, conversion factors are always equal to 1. So if you flip it, it's still equal to 1, right? Okay, so what's the molar mass of water? Well, 2 hydrogens and 1 oxygen, right? 2.02 plus 16 is 18.02. So we divide 18.02 into 50. And I get 2.7747. Right? Yeah. But we got to round to, remember, this is a conversion factor, so you don't even look at that. You look at this one. 3 significant figures. All right, so we got to chop it off there. 2.77 moles of water if you have 50 grams. All right. What did they round it? 2.7. I don't know. Some kind of rounding error. All right. Are you quiet because this is simple? Or is it snowing you? No, it's simple, right? Aspirin has a molecular formula of C9H8O4. C9H8O4. You know what the chemical name for aspirin is? They used to put it on the bottles, on some bottles. It's acetyl salicylic acid. Right? It was invented in Germany in the 1800s. I don't know how they discovered it was a good anti-inflammatory and good pain reliever. But you can find salicylates naturally, right, in all types of plants. All the mint family. You know how to recognize a mint family? It's got a square stem, and leaves are alternating opposite. Leaf here, and a leaf here, a leaf here. Right? And then, of course, if you crush it, you can smell it or taste it. But they have salicylates in them. They don't have this compound, but they do have salicylates that are effective against inflammation and pain. All right. What's the mass of 1 mole of aspirin? So what it's asking us for is the molar mass of aspirin, right? 9 times 12.01, 8 times 1.01, and 4 times 32 grams per mole. And that will be the molar mass of that compound. 180 grams, rounded off to 3 places. Okay. All right. All right. So when we write a chemical formula, wait a minute, we've named compounds, haven't we? Yeah, I know we have. Okay. Seems like we're backtracking a little bit. The subscripts in a chemical formula give the number of atoms of the various elements in the formula. So when we're talking about an ionic compound, where you have a metal and a nonmetal, we're actually describing a formula unit, right? Because we know ionic compounds don't come in discrete formulas like sodium chloride. It's not NaCl, and then there's another one over here. There's another one over there. It's a matrix of cations and anions. So we take the simplest whole number ratio, and when you determine the molar mass of sodium chloride, you're determining the molar mass of that formula unit, NaCl. Whereas with covalent compounds, where you have two nonmetals, you're determining the molar mass of a mole of those molecules. But you can still refer to it as a formula unit. Okay. So what we're looking at here is for N2O4, two nonmetals, that is a molecule, right? It's an independent unit that functions in whatever environment or reaction. It has 2 atoms of nitrogen, 4 atoms of oxygen. But if you have a mole of them, you have 2 moles of nitrogen and 4 moles of oxygen. Okay. They're making a distinction between the microscopic and the macroscopic view. Macroscopic is the one that you can measure on your balance. Microscopic is individual molecules or formula units. All right. How many moles of carbon atoms and hydrogen atoms are present in 2.5 mole sample of C2H6? So we got back to ethane, C2H6, 2.5 moles of that formula unit. And that's a molecule, right? It's a covalent compound. Okay, so they want to know carbon atoms and hydrogen atoms in a mole, in that many moles. All right. So there are a couple of ways you can approach this. One is you can say, all right, this formula unit has 2 carbons, right? So how many moles of carbon do you have? Well, you have 5 moles of carbon, right? And how many moles of hydrogen do you have? Well, what's 6 times 2.5? 15? 15 moles of hydrogen. Okay. Now they're asking us how many atoms in that many moles. So all you would need here is 5 moles times the equivalent of a mole. Right? Atoms. How many atoms in a mole? 6.022 times 10 to the 23rd. You could do the same thing for hydrogen, or substitute 15 in there. And that will give you the answer. Well, there it is. Oh, it doesn't. It wants us to use moles as our answer. Well, okay, we got it then. Rather than go all the way to the numbers of atoms, we're stopping at moles because that is a counting unit. All right, I took it too far. Let's see. In the molecular formula of aspirin, how many moles of carbon atoms, hydrogen atoms, and oxygen atoms are present? Well, 9, 8, and 4, right? Right, 9, 8, and 4. For each mole of that formula unit, you have 9 carbons, 8 hydrogens, and 4 oxygens. Okay. If you like flow charts, here it is. I'm not going to spend time on this. If you use the dimensional analysis procedure, rather than memorizing the flow chart, you just know what you're given, and you know what the target is, you know where you're going. Then you use conversion factors to cancel units and end up with the target units that you want. Right? Because there's your conversion factor or multiple factors. We covered that already in previous discussions. Didn't we do this one before? How much will it cost to drive from such and such to some other place? Didn't we do that? Yeah, I thought we did. Right, so I put this one together for Beckley to Atlanta because I got Ken in Atlanta. 385 miles there. How much money do I need to take? So I'm given 385 miles. I want to target how much money do I need in my pocket? Well, that's one way. So if my car gets 25 miles a gallon, that says that's how many gallons I need. What's the cost of gas? Not that anymore. Right? You have to substitute a bigger number in there. Let's see, I paid this morning three 56, I think, in Oceana. Between Beckley and here, Oceana's got the cheapest at present. It varies. Okay, so one way I need $43 under those conditions, and then you just double it and pad it maybe 10 or 15% for driving around money. Maybe 25% for Atlanta. You got to go half hour to get anywhere in Atlanta. Okay, which of the following is closest to the average mass of one atom of copper? I don't know why I leave this slide in there, because if you know how to take a test, you can figure that an atom's not going to weigh grams, that many grams, A, B, C, or D. Right? So E's got to be the answer. I didn't do a calculation with it, but maybe I should do. Average mass of one atom of copper. All right, so where are we starting with copper? One atom, isn't it? That's what we want to know, one atom. Well, let's keep it mathematical. One atom. Right? We don't have a conversion for mass, atom to mass, for copper. What we do have is mass and mole relationship. So we got to get this into moles. Moles per, excuse me, atoms. Atoms in 1 mole. Okay, that gets rid of atoms and leaves you with moles. Now I can make the conversion from moles to grams. For 1 mole, copper weighs what? See if I can see it through the shine. 63.55 grams per mole. That cancels moles. We did a chain conversion, and now we know that 1 atom weighs whatever that is. Well, there it is. 1.055 times 10 to the minus 22 grams. This is a trick question. How many copper atoms are in a 63.55 gram sample of copper? 1 mole. I just put it up here. That many copper atoms. All right. Now let's start comparing. Which of the following 100-gram samples contains the greatest number of atoms? Magnesium, zinc, and silver. Magnesium, zinc, and silver. And we've got 100 grams of each one. So which one has the largest number of atoms? How would you approach this? You got the same mass for each one. The largest number is the one that is the lightest one, because it takes more of them to make 100 grams, doesn't it? Yeah. So all we need to do is find out what the molar mass is for each one. Right? Magnesium is 2431 grams per mole. Zinc is right next door to copper. 6539. And silver. That's a big atom. 107.87. 107.87 grams per mole. Okay, so the one that requires the most atoms to make 100 grams is the lightest one. That one right there. The one that requires the least number is silver. All right. Now we're going to make it a little more difficult. Let's see. I'm going to leave those there because we've got the molar masses and put this one. ABC is 107.9 grams of silver, 70 grams of zinc, and magnesium is 21.0 grams of magnesium. All right, the question is, put them in rank of descending number of atoms. So the nice thing about just having 3 of them is if we can find out which one has the most number and which one has the least number, then we don't have to calculate the last one. But 107.9 grams of silver is what? Is it greater than a mole, less than a mole, or equal to a mole? It's equal to a mole, right? Based on that value. How about zinc? 70 grams of zinc is greater than a mole. And 21 grams of magnesium is less than a mole. Okay. So from greatest to least numbers under these circumstances, greater than a mole is zinc, and then 1 mole of silver, and then less than a mole is magnesium. So there's your order: zinc, silver, magnesium. Right. Well, BAC, the same thing. Okay. Time. I want to keep moving, but I don't want to move so fast that I'll lose you. All right. Consider these 4 compounds. We've got 100-gram samples of each. Rank them in descending order of number of oxygen atoms. All right. So let me see. Let me find a place where I've got enough room. About here. Water. What's N2O? Well, the proper name is dinitrogen monoxide, right? Right. If you've ever had your teeth worked on, I don't think most dentists don't use it, but oral surgeons do. Laughing gas. That's N2O. I never had it. Right. I had all my wisdom teeth taken out in the dentist chair with lots of Novocaine. And one of them was impacted, so we had to drill and break it. They don't do that anymore. I think there's like some lawyers got hold of them and decided there was too much risk. C3H6O2, C3H6O2, and CO2. Okay, we've got 100 grams of each. Now, if I didn't squeeze myself in too tight here, we've got 100 grams of each one. $100 grams. All right. We need to convert these to moles of oxygen so we can rank them. Right. So I use Henry Ford. This is my assembly line. I'm going to treat each one the same way. Only, unlike Ford, you can have any color you want as long as it's black. He actually said that. But now we've got different colors, we've got different accessories. So we're gonna send it through the same assembly line, but the things are going to change depending on what the customer wants. And in this case, we want to change grams to moles of water first. Right? So each one is going to require the molar mass. Grams on the bottom, moles on the top. For each mole, we have a mass here. We did this one earlier. It's 18.02. N2O. 2 times 14.01 is 28.02 for nitrogen, and then 16 for the oxygen. Is 30, let's see, let me do that one again. Doesn't look right. 14.01 times 2, and then 1 oxygen. That's better. 4402. This one I think is propionic acid. So we need 3 carbons. 12.01 times 3. 6 hydrogens. 1.01 times 6. And add that in. And then 2 oxygens. 16 plus 16 is 32. 7409. Okay, and carbon dioxide, 12.01 for the carbon, and then 2 oxygens is still 32. 4401. Okay. If we resolve this, that will give us moles of the compound. But we want moles of oxygen. So we need another conversion factor. This is moles of the compound for each one of these moles. So for the compound, we want it on the bottom. Compound, compound, compound. And on the top, we want oxygen, 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 oxygen. And this is still mole ratio. So the mole ratio here is, for every 1 compound, how many oxygens do you have? 1. Here, for every 1 compound, you have 1 oxygen. Here, for every 1 compound, you have 2 oxygens. And here, for every 1 compound, you have 2 oxygens. So that gets rid of the moles of the compound and leaves us with moles of oxygen. Good so far? Okay. So 100, oops, that's too many. There we go. Divided by 18.02 is, and times 1, right? Because it's 1 divided by 1. And this one is some 5.55. Well, it's 4 significant figures. 5.549. This is moles of oxygen. Okay. Now we got this one. 44.02 divided into 100 times 1 again, which is 2.272. Now we go back to 100 grams. Divide by 74.09. Now we got to multiply by 2 because of the ratio. 2 for every 1. 2.699. 2.699. And carbon dioxide, 144.01 divided into that, times 2 is 4.544. Okay, now we can put them in order. Descending order of number of oxygen. The most number of oxygens. Here, water. Second one, carbon dioxide. Third one, propionic acid. And the last one, N2O. Okay, that's how you do it. Good old Henry Ford. Never mind, he was a rabid racist and anti-Semite. That's beside the point. Okay. Consider separate 100-gram samples of each of the following and rank them in descending order of number of oxygen atoms. We already did that, didn't we? Yeah, we did that. How did I get that duplicate slide in there? Oh, this got the calculations for us. Here we go. Just checking my math. And then we rank them. There we go. I probably ought to throw that first slide out. Just leave this one in there. All right. Okay. The formula of aspirin is same as it was before. Calculate the number of molecules in 0.325 gram tablet of aspirin. That full strength aspirin is 325 milligrams. It'll say that on the bottle. If you buy aspirin, not the baby aspirin. Baby aspirin is 81 milligrams. I take one of those every morning. But the kind that you would take for adults and pain relief or anti-inflammatory would be 325 milligrams or 0.325 grams. All right, so we got another chain conversion there. We want to find out how many moles first, and then we convert that to molecules using Avogadro's number. Okay, and we get 1.09 times 10 to the 21st molecules in that sample. Now, that's not the only thing in that tablet. There are 325 milligrams of aspirin, but you have carriers in there. Right? All drugs are like that. They got active ingredients and what they call inactive ingredients. Okay. All right. I thought we balanced equations before. We didn't, did we? We haven't learned how to balance equations, have we? Have we? Let me do a quick check. Ooh. No, we haven't. My apologies. I thought we had. All right, I'm going to show you how to do it. Okay. All right. So a chemical equation is it's like a sentence. It has words in it, which are the compounds or the elements. And on the left-hand side, that the compounds or elements that are called reactants. Those that we put together and we expect them to do something. We're going to change their identity. All chemical reactions change the identity of the reactants into something else we call products. And in between, we add a plus sign. We got actually you can have one reactant. Some reactions just one reaction, and it decomposes into two or more products, like nitroglycerin. Right? It decomposes into nitrogen gas, oxygen gas, carbon dioxide gas, and let's see, I forget the fourth one. There's a fourth one, but it does it really quick, and that's why it's an explosive. Right? It goes from like 4 moles of nitroglycerin to 29 moles of gas, just like that, and that's what causes the force of explosion. Anyway, it's typical to write the reactants, and that's why I hammered so hard learning how to write compounds. If you get a word problem, say if I tell you I want you to write a chemical equation and balance it for calcium sulfide reacts with water and it produces calcium oxide and hydrogen sulfide. If I give you that in a sentence, you got to be able to write the compounds before you can write the equation and balance it. Right? And there's an arrow between them. Right? Actually, for now, we're going to let the arrow go one way. But in reality, the arrow can go both ways. So the products can turn around and go back to reactants. Some of them, not so much. Some of them, yeah, a lot. You get to reverse reaction. But for now, we're just going to stick a single arrow in there until we learn how to balance them. So, first of all, let me just write this equation up there. Calcium sulfide plus water yields calcium oxide plus hydrogen sulfide. Now, the way to tell whether that's balanced or not is to remember that this formula is 1 mole of that formula. So there's 1 mole of calcium, 1 mole of sulfur. 1 mole of this is 2 moles of hydrogen and 1 mole of oxygen. So do you have the same number moles of elements on the product side as you do on the reactant side? That's balanced. So we have 1 calcium here, 1 hydrogen, 1 calcium there, 1 sulfur there, 1 sulfur there, 2 oxygens here, hydrogens, and 1 oxygen. So that one's already balanced. We don't have to do anything to it. Now, once you've written the equation correctly, the compounds, elements, whatever the case may be, and put them in the formula, in the reaction equation, then I forgot where I was going with that. Oh, if you have to balance the equation from there to get the right number of elements on both sides, the only way to do it is with numbers in front of each of the compounds. We're called coefficients. You can't touch the subscripts anymore. That's 1, 1, 2, 1, 1, 1, 2, 1. Those are chiseled in stone. You don't touch them. Only the coefficients to balance an equation. Okay. And that's what this slide says. That number is placed to the left of each of the chemical formulas. And then with the coefficients, what you're saying is, if I have to put a 2 here, now I've got 2 moles of that compound. I've got 2 moles of calcium and 2 moles of sulfur. If I did that, then it would be out of balance because I only have 1 mole of calcium and 1 mole of sulfur on that side. Okay. And if you always think in terms of moles rather than atoms and molecules, then you're already 1 step toward using the balanced equation to do what we call stoichiometry, following the masses or volumes of gases, whatever the case may be, of reactants to products, and being able to determine what to expect in the products. Okay. We're headed there. Okay. This came from the authors of your textbook, and I'm going to leave them up there long enough to be recorded, but I'm not going to talk about them because I got a method. I probably ought to get rid of these slides. Most textbooks, most chemistry textbooks say once you've written the unbalanced equation, you balance it by inspection. And that's all they say about it. They might go into some, they might do something like this and give you guidelines, but they don't give you a procedure. And that's what I want to do. All right, these helpful hints, let's see. Did I give you a handout in balancing equations, didn't I already? No? Let's see here. I surely thought I did. Helpful hints. That's the one I wanted to give. Yeah, I gave you that one. Helpful hints. Yeah, okay. Yeah, that one right there. Does anybody need an extra copy? No, you're good? Okay. That's what I duplicated in these slides. Helpful hints. Now, they're in here for posterity's sake, but they're not going to mean much until we actually start balancing equations and I use them and tell you when I'm using them. All right. The first helpful hint is if you have an equation and one of the reactants or products, it doesn't matter which, is a single element, like this example is oxygen, leave that to last. Why? Because if you put a coefficient in front of that one, you only change that one. You don't change everything in a compound. Like carbon dioxide, if you put that 6 in front of CO2, you changed carbon and oxygen. So we save oxygen, in this case, till last. So that when we make the change on oxygen, we're not screwing up everything else we've done up to that point. Okay. As a general rule, if there's water, you usually save that one till next to the last. But that's not always a hard and fast rule. It's just a suggestion. Sometimes, now, when we have a balanced equation, we want whole number coefficients. And remember, if there's not a number there, there's a 1. It's understood. Because if you put the formula there, you got to have at least one of them, right? So we don't write a 1 there. So that's 1, 1, 1, and 1. But if we need a certain number, in this case, oxygen, but we can't do it with a whole number. What we're shooting for is whole number coefficients. The simplest whole number coefficients gives us the ratio of each one of these to another. Right? So in this case, it's 1 to 1 to 1 to 1. But it could be something else. In the case there, it's 2, 25, 16, and 18. But in order to get there, we may have to use a fraction. Right? In this case, we use 25 halves of oxygen because we only needed 25 oxygens to balance the oxygens from the reactants, the product side. Right? Count them up. 2 times 8, carbon dioxide. 16 plus 9 is 25, right? That's 25 oxygens on the product side. Well, we need 25 on the reactant side. Right? But we can't get it with a whole number because oxygen is a diatomic element, right? 2 times anything is what? An even number, isn't it? Right? We don't need an even number. We need 25. So if we take 25 halves of oxygen, right? If you have 25 oxygens down here, right? They're like that. 25 of those, and you take half of them. Half of these molecules, how many oxygens do you have? 25. Just take half of them, and you got 25. That's why we had 25 halves. So 25 halves of O2 is 25 oxygen atoms. That balances the equation, but we don't want to leave it there. So what we do is, now that we have the exact ratio of octane, oxygen, carbon dioxide, and water in this equation, we multiply the whole equation through by some value. You can do that in math, right? If you multiply the whole equation through by, or divide by, doesn't matter, you've got the same equation as you had before, correct? That's math. So if we multiply the whole thing through by 2 that we see here in the second step, then we put a 2 in front of the octane. We cancel the 2 here, right? 2 in the numerator, 2 in the denominator, cancel, and it gives us 25. And then 2 times 8 is 16, and 2 times 9 is 18. So that's where the whole number ratio comes from in that final equation. We have canceled out the fraction that we used as an intermediate step. Okay? We'll do one like that. This one is a little more problematic. In this case, we've got an element that occurs in one place on either side. Let's see. That's not a good example. Just it's the correct hint, but that's not as good example as I thought it was originally. So we'll come across one of those and I'll show you when it happens. Okay. The last useful, helpful hint is polyatomics. If you have an equation with reactants and products where the polyatomics are the same on both sides, some reactions take polyatomics and rip them apart. Right? But if they don't, if the polyatomic stays intact for reactants and products, you can use that as a balancing unit. And that's what this table is going to show you, right? Ammonium and phosphate are the same on both sides, right? We didn't tear them apart. So we're going to use those as balancing units. That simplifies the whole process. Right? First, we do a count. What's our initial count? Well, 3 ammonias, right? See that subscript? We got 3 ammonias. We've got 1 phosphate. We've got 1 calcium and 2 chlorides. Okay, that's our initial count. And we do the same thing on the other side. The beauty to this method, that I call my budget method, is that you can instantly see when you're not balanced or when you are balanced in each step. Okay. Now, the next one is a little problematic and takes some intuition. Where do you start? Where do you start changing coefficients to make things balance? Well, with practice, you sort of get a feel for it. But if you don't know, if you don't have any idea, just start at the top. In this case, I started with calcium. Right? So if I put a 3 in front of the calcium, I get 3 calciums on the reactant side and 3 calciums on the product side. So calciums are technically balanced at this point. But that makes 6 chlorides. Right? So the chlorides are out of balance. So the next step, I go over here to the other side and I put a 6 in front of the ammonium chloride. That gives me 6 chlorides. But now I've got 6 ammoniums on the reactant side. So I need to put a 2 in front of the ammonium phosphate to give me 6 ammoniums. And that changes the phosphates too. Well, abracadabra, right? It's balanced. And you can see that. 6236, 6236 on both sides. Okay? We'll do some other examples. Well, I'm not going to do a review with you. It's going to be a video. But there are lots of examples in the review document and on the video to show you how to do those. You need to practice it. If you don't practice it, it will just overwhelm you. You'll get in there and start messing around and you'll go in circles. Usually, if your equation never balances, go back and be sure that you've written the compounds correctly. If it doesn't balance, then they might not be written right. All right. So calcium oxide plus carbon yields calcium carbide plus carbon dioxide. In this case, which is correctly balanced? Well, let me see. This is a simple one. Why don't we use this as our example? So you start with the unbalanced equation. Calcium oxide. Some of these, you'll eventually figure out that you don't have to use the budget method. I mean, you can just do it like that. But the budget method is the safe way to do it. Carbon dioxide. Okay, so we do a count. We've got calcium. That's a carbon. We got calcium, oxygen, and carbon. Calcium, oxygen, carbon. We've accounted for all the elements or polyatomics. Now we do our count. 1 calcium, 1 oxygen, 1 carbon. On this side, we have 1 calcium, we have 2 oxygens, and we have 3 carbons. Okay? Now, first hint, we've got an element here. Do the carbon last. So we're not going to tackle carbon first. We're going to tackle oxygen first. So we've got 2 oxygens over here. We need 2 oxygens over here. 2 oxygens. That gives us 2 calciums. Okay? Now we need 2 calciums over here. So that gives us 2 calciums, but that gives us, let's see, 4 plus 1 carbon is 5 carbons. Right? Okay. Now, how are we going to get? We need 5 carbons. Oh, we just put a 5 over here, don't we? That's why we save carbon to the last. Right? 225, 225. So this is the simplest whole number ratio, and you know because you can't divide it through by any number, whole number, and simplify it further. Right? 2, 5, 2, 1. I mean, we got 2 prime numbers in there. Actually, like they're all prime numbers. So you're not going to find anything that'll divide through there and simplify it. So that's our balanced equation. Right? That's the best one. Now, the others have the proper ratio. Roman numeral 3, yeah, it's got the correct ratio. It just uses fractions. Right? And the last one, I think, also. No, the last one's not right. How about the first one? No, the first one's not right. Okay, 2 and 3 are technically correct, but 3 is not the ideal because it's fractional. So we're going to use 2, simplest whole number coefficient ratios. Which is true following? Which of the following is or are true concerning balanced chemical equations? There could be more than one. The number of molecules is conserved. Did we do that? All you need is one example that blows that out of the water. Molecules conserved. Numbers of molecules on this side, 7, right? 2 plus 5. Numbers of molecules on this side, 2 plus 1 is 3. No, molecules are not conserved. Coefficients tell you how much of each substance you have. That's a little misleading. What we mean by much is usually mass. How much of each one? No. Balanced equations tell you how many moles of each one you have. Right? That's it, counting. So 2 is false. Atoms are neither created nor destroyed. Well, that's true. Right? That's been true for, I don't know, 4 centuries. Coefficients indicate the mass ratios? No. Mole ratios only. And 5, the sum of the coefficients on the reactant side equals the sum on the product side. That's another way of saying Roman numeral 2, and it's wrong. So the only one that's true out of those statements is Roman numeral 3. Okay, so here's one. Actually, they're kind enough to give us A, B, C, or D, but it's a word problem. And if you're given the word problem and you're not given choices, then you've got to know how to write these compounds. And in this case, what's the correct balanced chemical equation for the process of heating sodium bicarbonate? They're using the old name. That should be changed to sodium hydrogen carbonate. Sodium hydrogen carbonate. This is a polyatomic ion. Right? Just look in your list. That list I gave you with the polyatomics. And this is going to yield, upon heating, this is one of those where you have one reactant. Decomposes. And it decomposes into sodium carbonate. How do you write that? Well, carbonate is a 2- charge on its polyatomic ion. Sodium is an alkali metal, it's only +1. So you need 2 of them to balance. Plus what? Carbon dioxide and water. Let's see, I need to leave some room in here, don't I? There we go. Okay. So notice that we can't hold the polyatomics as balancing units because it got ripped apart. Okay. So we have to account for everything individually. Sodium, hydrogen, carbon, and oxygen. So on this side, we have one of those, one of those, one of those, and 3 of those. 3 oxygens. On this side, we have sodiums, 2 sodiums, hydrogens, 2 hydrogens, carbons, 1, 2, and oxygens, 3, 4, 5, 6. Okay. We don't have any elements that we can hold till last. We do have water, so we may want to hang on to water for a while. So how about the carbons? Right? You got 2 carbons on this side. Maybe we need 2 carbons on this side. Right? That'll give us 2 carbons. It gives us 2 sodiums. And that'll give us 2 hydrogens and 6 oxygens, right? Did I count it wrong? Let's see. 2 sodiums, 2 hydrogens, 2 carbons. Yeah, 6 oxygens. There we go. How about this side? Did I do that right? 2 carbons, hydrogens, 2 hydrogens, 3, 4, 5, 6. Yeah, that's right. I'm sorry? 3, 4, 5, 6.
Oh, never. I thought you had it.
Not yet. Okay, so these are all right. See, that one's right. Oh, we're done. 2, 2, 2, and 6. That's all it took. Just one coefficient balanced the whole equation. Right. And if you didn't have the budget set up, you'd have to go through and in your head say, and see if it's all right. Which, I mean, some people can do that, but I get confused on, especially on very complex reactions. All right, so that means C is the best answer for this one. I had my general chemistry class do this one. Or did we do waters of hydration? We didn't do that one yet. Let me see, is that one that we're going to do? Oh, no, you don't get to do that one. My general chemistry class does. I'm not going to spend any time on that. But we do this reaction in class and actually try to figure out the products. Okay. No questions? Better. This is working better. We're doing on time. 10:30. 10:50 is when this is supposed to transition to the lab. All right, coefficients in a balanced chemical equation. 4 molecules of iron react with 3 molecules of O2 to produce 2 molecules of Fe2O3. That's technically true, but it's not very useful, right? If you think in terms of moles, it's more useful because moles can be converted into grams if you need it. Okay. But what we're going to do is take a balanced equation. Let me write that balanced equation up here again. 4 Fe plus 3O2 yields Fe2O3. 2 of these. Okay. We're going to use the balanced equation to generate a conversion factor. If you know that you have, let's just take, say, 8 moles. 8 moles of iron. And it reacts with, let's just say, excess. You got plenty of oxygen, you don't have to worry about it. We're going to use up all the iron and produce Fe2O3. Right. If you start with 8 moles, how many moles of this one are you going to produce? We use a conversion factor. This is that many moles of iron. Our conversion factor takes moles of iron and cancels them and leaves us with moles of Fe2O3. And the numbers that go in here are the coefficients. So 2 here and 4 here. So we have 4 moles of Fe2O3. Okay. And once you balance your equation, these coefficients can be used to generate conversion factors to go from one place to another. In other words, and actually this is a hard and fast rule, you can't move anywhere in that equation unless you have moles. If you got grams, you're stuck. If you got liters of a gas, you're stuck. It has to be converted to moles before you can go from here to here. Think of it as a great wall. Right? You can't get over or under that wall unless you're moles. Okay. All right. And that's what we did there. That's an example. I'm going to skip that one. Let's see. We're kind of getting short on time, so there's the answer to that one. You can satisfy yourself. What we're getting into now is stoichiometric calculations. Stoichiometry means keeping track of your reactants and products, right? It's derived from some German words, but basically means that you can use a balanced equation to determine the outcome of a reaction. That's our stoichiometry. And I'm going to skip over that one too. Now, this is a pretty difficult, I don't know why I let this one pass, but it can teach you a lot about using balanced equations for the purpose of stoichiometry, following reactants to products. So this exercise says if you have methane and react it with oxygen to produce carbon dioxide and water, but you also, in a separate reaction, you have ammonia reacting with oxygen to give you nitrogen monoxide and water. First, we want to write the balanced equations, and then we'll slip the stoichiometry in on you. So let's say, let's try it over here like this. Methane, right? So they actually give you the formula for methane plus oxygen yields carbon dioxide and water. So we need to balance that equation, right? Now, I'm going to use the budget method just because we're learning how to use it. Carbon, hydrogen, oxygen. So we have 1 carbon, 4 hydrogens, 2 oxygens on this side. And on this side, we start off with 1 carbon, 2 hydrogens, and 3 oxygens. Right, we're going to hold the oxygen till last. So let's see, carbons are okay. How about hydrogens? Well, let's see, we have 2 here and 4 there. So if we put a 2 there, that'll give us 4 hydrogens. But it'll also give us 2 plus 2 is 4 oxygens. Now, if we put a 2 in front of this one, that gives us 4 oxygens. So 1, 4, 4, 1, 4, 4. That was balanced. Okay. The second one is ammonia plus oxygen yields nitrogen monoxide plus water, I think. Yeah. In this case, we have nitrogen, hydrogen, and oxygen. So our initial count is 1 nitrogen, 3 hydrogens, 2 oxygens on the reactant side. On the product side, we have 1 nitrogen, 2 hydrogens, and 2 oxygens. Oh, this is okay. This is one of those helpful hints or tricks that I sort of glossed over before. In this case, we're going to hold the oxygens to last, but we have hydrogens. We have hydrogen in one place here, hydrogen in one place there. That one's an odd, and this is an even. Right? So we could multiply this one by 2 and get 4, but that doesn't help us. We can multiply this one times 3 and get 6, but that doesn't help us. But if you have a coefficient here of 2 and 1 there of 3, try cross multiply. Take that 2 and put it over here for the hydrogen, and take that 3 and put it over here. Okay, So in one operation, we use two coefficients. And that gives us 6 hydrogens here and 6 hydrogens here. Now it also changes the oxygens, like 3 plus 1 is 4 oxygens. And over here, it doesn't change oxygens, it changes nitrogens. Here we go. 2 nitrogens. Okay. So now we can go to nitrogens because we want to leave oxygens till last. So we need 2 nitrogens. Right? 2 nitrogens. But that gives us 2 plus 3, correct? 6 oxygens. No, 5, excuse me. Yeah, I can't even add. 5 oxygens. Okay, now we need the other trick, the fraction, intermediate fraction step. Because we've got a 5 here and a 2 there. We got a 2 here. You can't multiply that by any whole number and get 5. We have to multiply by a fraction. So 5 halves will give us 5 oxygens. Okay. Now technically we're balanced. Because you can see it here, 265, 265. But we don't want a fraction in our equation. We want a whole number. So now you can remove the budget. It's done its job. And the next thing you want to do is get rid of that fraction. So how do you get rid of a half? Multiply by 2. The whole equation through. We can do that because the ratios are fixed. And if we multiply by the same number through the whole equation, the ratios are intact. So this becomes a 4. This becomes a 5. This becomes a 4. And this becomes a 6. Okay? Now let's clean it up. This is going to be a 4. This is going to be a 5. This is a 4. And this is a 6. There we go. Okay, now we have our balanced equations. That looks like a sulfur, doesn't it? Right there. There we go. Okay, step 1, balance the equations. Does anybody have questions about that? I know it kind of blew pretty fast. Okay, 4, 5, 4, and 6. 4, 5, 4, and 6. 2, 1, 2, 1. There we go. Okay, next. The question is, what mass of ammonia would produce the same amount of water as 1 gram of methane? So if we have 1 gram of methane, we're going to produce a certain amount of water. We want to know how much ammonia would give you the same amount of water. So the connection is by way of the waters. Okay, if we have 1 gram, let's put it up here. 1 gram of methane. We want to convert that to moles. Why? Because without moles, you're stuck. You can't move anywhere in the balanced equation unless you're moles. So we got to convert this to moles. Grams per mole, right? Get rid of the grams, leave you with moles. So what's the magic number? 12.01 for carbon and 4 times 1.01 for the hydrogens. 16.05. So we divide that into 1, just take the reciprocal actually. 6.23 times 10 to the minus 2. 6.23 times 10 to the minus 2 moles of methane. Now that we know how much methane is being used, and there's excess oxygen, it says so right there. So we don't have to worry about the oxygen. We want to convert that to how many moles of water? Well, 6.23 times 10 to the minus 2 moles of methane. We need a conversion factor that will give us moles of water. So we want water on the top, moles of water on the top, moles of methane on the bottom. The magic numbers, 2 to 1. 2 waters to 1 methane. So 2 times that value is how many moles of water are produced. 1.25 times 10 to the minus 1. Minus 1 moles of water are produced with 1 gram of methane. Now, we want the same amount of water here, don't we? If I nod, yeah. We want the same amount of water here. So we have the same amount of water there. Now we want to convert it. How many moles of ammonia were required to produce that much water? So we take this value and we need a conversion factor. That'll be moles of water gives us moles of ammonia. And here the magic numbers are different. 6 waters for every 4 ammonias, the coefficients. So that cancels the moles of water, gives us moles of methane. We need 4/6 or 2/3 times that value. And that's 8.31 times 10 to the minus 2. 8.31 times 10 to the minus 2 moles of ammonia. Now we convert it back to grams. Another conversion factor, moles to grams, right? Grams and moles in a quotient, that's molar mass. What's the molar mass of ammonia? 14.01 for nitrogen and 3 times hydrogen. 3.03, right? I think I can do that in my head. 17.04. Right? Moles cancel, leaves us with grams of ammonia. Let's see. I get 1.42. 1.42 grams of ammonia. So what we're saying is 1.42 grams of ammonia will give you exactly the same amount of water as 1 gram of methane burned in air, both of them burned in air. Let's see, did I animate it? Yeah, I animated it. Okay, so there's the moles of methane. We're going to convert it to moles of water. Then we're going to take that same number of moles of water and convert it back to ammonia and convert the ammonia to grams. Okay, that's stoichiometry. Now, a taste of reality. What we've been talking about up to now concerning stoichiometry is theoretical. It's based on the balanced equation. If we get complete conversion of product, of reactant to product, then we calculate those values. But in reality, you never get that. Some reactions are really cooperative. They'll be over 90% conversion. So if you think you're expecting 100 grams of product, you'll get 90 grams of product actually. And various factors contributed to that. Side reactions that just eat up your reactant and take it to something else. Purification processes, losses there. So these are empirically determined values. The actual yield versus the theoretical yield. And if you know the actual yield, usually in terms of mass, but not always. And then the theoretical yield times 100, that gives you percent yield. Now, Fritz Haber, when he was developing the Haber-Bosch process, where you take nitrogen gas, combine it with hydrogen gas, and get ammonia. And he was doing that actually for intellectual purposes, but as it turned out, it was useful for the Germans. Because during World War I, when it started, the Allies embargoed nitrates from Chile. Chile had hundreds of feet deep of bird and bat guano had built up on the coast of Chile over the centuries, and that was a good source of nitrates to make gunpowder. But Germany couldn't get hold of it anymore. So Fritz Haber came along and he took nitrogen from the air, combined it with hydrogen, make ammonia, and from ammonia you can make nitrates, and there you go. You can make your gunpowder or your nitrocellulose, whichever the case. But his problem was very, very low efficiency of that conversion. So he had to figure that one out. He eventually got it up to about 15%. And then by recycling reactants, removing the product ammonia and then recycling reactants, and keep doing that several times, he increased the output, the yield, to something that was economical. Anyway, that's a simple calculation, right? That's what it means. That calculation can be used just like anything, like density. Density equals mass divided by volume. Well, percent yields equals actual divided by theoretical times 100. Right? It's just an equation. So what would be the percent yield of a product for the theoretical yield and actual yield, respectively, as 5.6 and 4.5? So you're expecting 100% is 5.6 grams, but you're only getting 4.5. We just divide 4.5 by 5.6 times 100, and you get 80%. That's pretty good yield, actually. All right. I got a few more minutes, and we're down to our concept question, so I think this is probably the end of the slide set. Pennies produced prior to 1982 were composed of 95% copper. Did you know that? In 1982, the government decided to adulterate our coinage. It cost too much to make a copper, make 1 penny. It cost probably a dime to make a penny because of the cost of copper. So what'd they do? Well, they stamped out blanks of zinc and just coated them in copper. And that's from 1983 on, that's what you got. They did the same thing with silver money too. Right? If you find a dime with a Liberty head on it, then it was probably made before 1982. And it's going to be 95% silver. Anything after that is going to have just a little bit of silver, enough to make it look silver. Or if you take quarters or half dollars, turn them on their side, what do you see? You see 2 layers, don't you? Right? So they just stamped them together, the expensive stuff with the cheap stuff. And that's called, in economic terms, that's called adulteration of the currency. Okay, on average, these pennies weighed 3.11 grams. Let's see. Let's make some space and get rid of the distractions here. All right. 3.11 grams. That's the mass of the copper coin. How much of that is copper? 95%. So what's the fractional equivalent of 95%? Yeah. Thank you. There we go. That tells you how much is actually copper. Right? The rest is something else. Probably zinc. Okay, so that gives you the mass of copper. Well, once we have the mass of copper, we want to know, the question is how many atoms of copper are present. So we have to go to moles first. Get rid of the grams, leave us with moles. And copper was 65 point, go ahead, 55, 63.55, excuse me, 63, I'm thinking of zinc, 63.55 grams of copper per mole. So it gets rid of grams, leaves moles. Now we can convert moles to atoms with Avogadro's number. I didn't mention that before. That number, 6.022 times 10 to the 23rd, is officially Avogadro's number. Now, Avogadro never determined that number. It's an honorary name. Because it's based upon his theories. Remember the where you have two gases with the same temperature, same pressure, same pressure, temperature, and volume, then you have the same number of moles of atoms of the gas in those two containers. Doesn't matter what the gas is. And that led to our ability to calculate this value. So they put his name on it. 6.022 times 10 to the 23rd. Okay. And you just cancel those units and multiply it out. And your answer should be, oh, it's animated for me. Go. There we go. 2.8 times 10 to the 22nd atoms of copper. Let's see. We've probably got these concept questions usually come in pairs. Yeah. Let me see. A 2-liter bottle of carbonated soda has, on an equivalent average, 0.2 grams of glucose per 100 milliliters. Glucose is metabolized in the human body to the, according to the equation C6H12O6, that's glucose. Actually, it's a bunch of hexoses, but we're calling it glucose. That's the formula. And your body combines it with oxygen and makes carbon dioxide and water. You didn't know that, did you? Or maybe you did. Right. If you've had anatomy and physiology or basic biology course, they usually cover that. Only if we take glucose or table sugar for demonstration purposes and put it in a spoon and put a flame under it, you can set it on fire and it'll burn right there in that spoon. And it'll convert into carbon dioxide and water. It'll evolve a lot of heat, right? But your body can't stand that, right? We have a very narrow range of temperature under which homeostasis is active. So if we did it the way that you do it in the spoon, your body would burn up. So your body takes glucose and it goes through steps, right? Stepped reactions, intermediate reactions, where a little bit of energy is released and that energy is captured in usually ATP molecules, but usually sometimes some others. And eventually it produces the same amount of heat, same amount of energy, but it's captured along the way. But the overall equation is exactly the same. So use the following steps to determine the number of grams of carbon dioxide produced after the consumption of 10 2-liter bottles of carbonated soda. Okay, I'm supposed to stop now. You want to continue? Let me see if it's animated. Okay, there's the balanced equation. You can use the budget method and you find out that 1 mole of glucose plus 6 moles of oxygen yields 6 moles of carbon dioxide and 6 moles of water. That's a balanced equation. Now, what are we given? Well, we're given 0.2 grams of glucose per 100 mils. We want to convert that to how many moles of glucose. There it is. So first we've got to convert the, okay, we've got grams of glucose per 100 mils. You've got 2 units of measure. Remember how you deal with that? 1 unit at a time. So in this case, we're going to convert the milliliters into liters and then multiply that times a 20-liter bottle. Excuse me. Ooh, is that a mistake? No, 10 bottles, right? 2-liter bottles, right? Yeah, they're at the bottom. 10 2-liter bottles. So that's why it's 20 liters. And if we multiply that times the value that we just converted, that gives us the total mass of glucose that's been consumed. Then you can take that mass and convert it into moles of glucose, convert that into carbon dioxide using your stoichiometric coefficients, and then convert the moles into grams. 44 grams per mole is carbon dioxide, and you have 59 grams of carbon dioxide produced if you consume 10 2-liter bottles. Okay? And where does that carbon dioxide go? Anybody had anatomy and physiology in here? No? Okay. Where does that carbon dioxide go? Right out your mouth, from your lungs. Now, some of it on the way is used in the carbonate buffering system, right, to keep your blood pH, right, where between two numbers. You don't remember that one? 7.35, 7.45. That's a very narrow range of pH for your blood. If it goes below 7.35, you're in a state of acidosis, right, and that can be dangerous. Or you can go the other way. You can alkalosis be just as bad. And the alkalosis part is a problem for diabetics because of what they have to metabolize. They can't metabolize glucose because their cells won't accept it. Right? Without insulin, glucose won't go into the cells where they can burn it. So their bodies start metabolizing other things like ketones and acids. And they produce byproducts that drive the pH of their blood down. And they go into a state of ketoacidosis. Right? And if their blood sugar is high, like 4, 5, 6, 7, I've heard of 800, what is that, milligrams per deciliter, I think it is. If it goes that high, you better get them to the hospital right away. And if you have time on the way, smell their breath. You'll smell acetone, right? Because without glucose, they gotta need something. So their body's going to go to the next best thing, only it's not healthy. I'm sorry? 7.35 to 7.45. Yeah. You should get that in anatomy and physiology class. Or if you've taken EMT class of any kind, they should give it to you there too. Some biology classes will, if they use it as an example for homeostasis. Know what homeostasis is? Yeah. It's like maintaining, right? Like going into your body's in a state of chemical zen. Okay, that's it for chapter 6. And so again, I'm not going to be here next Friday. That's my day off. I've got to be in Beckley because my other boss says we're having a faculty staff institute. You better be there. So I got to be there. So on that day or anytime in between, go to Brightspace to the EXAM2 module, and you'll see a video link for last spring and a review. It'll be called a review. Okay, and that'll review you using that list of review problems that I handed out. Okay, it'll work from there. Okay, and if they give you problems, contact me. We'll work something out. If you know somebody else is having exactly the same problems, then we can get them all together and do a Zoom session and work through those problems. Okay. So anybody need to take a break before we do the lab?
Yeah.
Separating binary mixtures. It's going to be our lab. I see the water is kind of warm. I'm going to crank it up a little bit. And we'll talk about that as soon as you get back. Let's see, we're going to do next the lab. Let's see, this is lab number 4. All right, you want to look at the pre-lab questions?
Yeah.
Can I get an amen? All right. So, well, we can't do this one now. Read an authoritative source for discussion of filtration. Not Wikipedia. What's the physical property that allows filtration to work? It's particle size, right? Something that's small enough to go through the pores of your filter won't be retained, but something that's large enough that won't go through the pores will be retained. And in our case, that's the sand. It's a big enough particle that it'll be retained by the filter paper. So that's basically what any authoritative source will tell you. And you can get different grades of filter paper. Some can be big pores, so they'll filter really fast. They can be small pores, so they'll catch really small particulates, but it takes a long time to filter. So in those cases, we usually have a flask on the bottom with a side arm, and it leads to a vacuum pump. And you just evacuate the bottom inside the flask, and the differential pressure between outside and inside is increased, and it drives the filtration faster. It's called vacuum filtration. Okay, number 2 then. We'll look at number 2. What safety precautions should be taken when evaporating the filtrate containing sodium chloride? So maybe we ought to talk about the overall procedure, right? What are we going to do? We're going to take a sample of our mixture, sample mixture, and we're going to determine its, actually, we're going to weigh it, but we're going to get a mass. That's the total mass of the sample. And I've got them in little polystyrene cups here, labeled for your groups. Like, so if you look for your group label, 1 through 5, and grab that cup. Now, what we need to know is the initial mass of that mixture, right? Because that's going to be in the denominator for determining the percent of each one, of each component. So how do you determine the total mass? Well, the best way to do it, one way to do it, well, let me see, how do they want you to do it? Data sheet. Mass of the vial plus the sample. Right? So you take that sample and find its mass, total mass. Then you empty the contents into the beaker that you're going to add water to and dissolve the salt. So when you pour it in there, then you take the empty beaker, that little plastic beaker, weigh it again. And the mass of the sample that you put in the glass beaker for extraction, the difference between those two masses is what you dumped into the container. That's why they want mass of the vial plus the sample, and then mass of the empty vial. Okay, then you just subtract the smaller one from the larger one, and that's the mass of your sample. That's what you get first right here. Total mass of your sample. That mixture. Then you're going to put this into a beaker. What size beaker? 150 mil, I think. Is that right? Put it in your beaker and add water. So much water, whatever it says. The amount of water is almost immaterial. Just enough water to dissolve the salt. Now, is it going to dissolve the sand? No. We're going to dissolve the salt in water and then filter it. Then you filter and catch the filtrate. The filtrate, the stuff that goes through the filter, contains the sodium chloride. Right? The stuff that stays in the filter is the sand. So now you got two streams. Right? You got the filtrate, and you got the, wait a minute. I got to use the right terminology. Yeah, filtrate. Residue. And then you got the residue. This is the sand that's caught in the filter. And this filtrate is the sodium chloride solution. Okay. Now, this one, all you have to do is put that on the hot plate and heat it and evaporate the water. But before you can do that, what do you need to know? You need to know the mass of the beaker beforehand, the mass of the dry beaker. Because when you put that filtrate in it and evaporate the water, what's left is the salt. And if you weigh it afterwards, then the difference in the mass between this one and that one is the mass of the salt. Okay? Always think about the container. You gotta think ahead so that you can subtract out the weight of the container, because most often you want the mass of the contents anyway. So that subtraction gives you the mass of the sodium chloride once it's dried. Okay, the residue is caught on the filter paper. So in order to know the container on that one, you're gonna need the mass of the watch glass, which is just a curved piece of glass that sits on top of that boiling water. It heats up, plus the filter paper. Okay, beforehand. Then you weigh it after, and after it has the sand in it, the dried sand. So you subtract the two. Now you have the weight of the sand. Okay. So if you have, after you've dried it, you have the weight of the sand, the mass of the sand. You have the mass of the sodium chloride, and you ratio each one to the total mass times 100, and that gives you your percent composition for each one. It's really a simple procedure if you don't overthink it. But what most students fail to do is get those masses beforehand so that they can subtract the mass of the container from the total and get the mass of the contents. That's where you mess up if you don't think ahead and do that. Now, the instructions tell you to do it, but that's no guarantee. Okay, so now we can go back to the questions. With all these steps in mind, what safety precautions should be taken when evaporating the filtrate containing sodium chloride? Well, you're going to be using a hot source, aren't you? Yeah, right. Don't touch the hot stuff, or wear protection. right? I've got gloves up here of 4 different sizes. I couldn't find any around here, so I brought some from Beckley. So you've got a heat source that you have to be careful about. Okay. In addition to that, it's not just the hot plate, but as it evaporates, you're still dealing with steam that's coming off of that hot plate, right, as you evaporate the water. The other thing is, if you heat it, you can heat it pretty high in the beginning, right, when there's a lot of water to absorb the energy from the hot plate. But once it gets down to the bottom, when you just got a little bit of water left, moisture in the sand, no, sodium chloride, moisture in the sodium chloride, excess heat will start causing it to sputter, and it'll blow things out in your face. So you've got to watch for, what do we call it? Splattering. So as you get down lower in volume, the instructions tell you to start decreasing the heat as you get close to the bottom when you're finishing drying it out. Okay. So in order to help you with all these is wear your PPE, personal protection equipment, eye covering, lab coats, and gloves, right? Nitrile gloves I've got right here. Okay. Now about 3. What does 3 say? 3 comes in parts. 3.1. Define the following terms as they apply to this experiment. Homogeneous mixture. What would be a homogeneous mixture?
Mixtures that appear to be uniform throughout.
Right. There's another name for it too. A solution. Where do we see a solution in any of this? Right here. Right. When you filter that, when you mix the water in to your mixture, it dissolves the sodium chloride, but not the sand. And then you filter it through, and that gives you a solution of sodium chloride. Okay. About 2. Evaporation. What do we mean by evaporation? Well, technically, yeah, that's true. Yeah. You're converting a liquid to a gas. In this case, we're converting liquid water into water vapor to remove it from our samples. Okay. 3, residue. All right, we mentioned that before. Residue is here. What's retained in the filter paper? Now, residue can be applied in other circumstances, but specific to this experiment, it's what is retained in the filter paper. All right. Number 4.
What would you say residue was again?
Residue is what's retained in the filter paper, as opposed to the filtrate, what goes through the paper. Is that the proper name? Yeah, filtrate. I like to use their terminology when I can. Yeah, filtrate. Filtrate goes through the paper, residue stays in the paper. Okay, 4. A student was asked to determine the percentage of each component in a mixture of sodium nitrate and calcium carbonate. The mass of the sample used was 2.21 grams. So 4, the total mass equals 2.21 grams. That's the mixture. The student extracted sodium nitrate from the mixture with water and separated the insoluble calcium carbonate from the solution by filtration. Okay. That's similar to what we're doing. After evaporating the filtrate contains sodium nitrate. The sodium nitrate found to weigh 0.43. Sodium nitrate is 0.43 grams. And the insoluble residue is 1.67 grams, calcium carbonate. 1.67 grams. Okay. Next page. All right, calculate the percent sodium nitrate in the mixture. You just take this number, divide it by the total, times 100. That. Okay. B, that was A. B is calcium carbonate. Do the same thing with calcium carbonate, 2.21, and then times that. There we go. And then parentheses 2, calculate the total mass of the sodium nitrate and calcium carbonate recovered. So the recovered mass is this one plus this one. All right, so that's 0. And carry your 1, that's 1, and carry your 1, that's 2. 2.10 grams. So we didn't get it all back, did we? Right? Should be 2.21 grams. We only got 2.1. So what's the percent recovery? Well, it's just 2.10 grams divided by 2.21 times 100. Whatever that value is. Right. What's the percent error for separation? The percent error is this value, percent recovery, 100 minus that value. And that'll be your percent error. Okay. Oh, that's it. That's all the pre-lab questions. Those calculations are the same ones that you're going to be doing with the data that you collect today. That's why the pre-lab questions are in there, I guess, give you practice.